Hello everyone. So today I'm back again with the topic thermodynamics. I started teaching the very fundamentals, the first law in my first lecture. If you want to listen at those lecture, please go to my channel and watch the playlist thermodynamics. Okay, so today I will continue discussion on some of the fundamental topics of thermodynamics. Before going into details, I would like to teach a few words, a few topics, the definitions and basic concepts, the fundamentals. Okay, so let's get started. Let me share the screen. So, as if you do not know about the details of my research area, please check these details in my LinkedIn profile, my Google Scholar, and my ResearchGate profile. So, let's get started. So, as I discussed in the first law, Q equals uh, W plus dU, where Q is the heat supplied and W is the work done on the system and dU is the internal energy change. So there were two basic things in the first law, that is heat and work. So what is heat and work? So first let me discuss about work. So whenever a object is displaced through a distance dx against a force F, then the work done will on the system will be W equals F into dx. Like if you are trying to move a particle a distance dx against a force F, then the work done on the particle, that would be W equals F into dx. And there are different type of works, like mechanical work. Like if we are trying to increase the volume of a system from V1 to V2 at constant pressure, in that case the work will be mechanical work. So that work is equals to P pressure into dV, the change in the volume. If we are trying to uh, uh, do some gravitational work, that is we are if we are throwing a stone from a height h, it is dropping at the bottom and it is traveling, if suppose h distance, in that case the gravitational work, because this we are throwing a stone and some work is needed so that it can reach at the bottom. So in that case, the work will be gravitational work, that is equals to mgh, where m equals to mass of the system, g equals to gravitational force, and h is the height which the particle has traveled. Next, electrical work. Suppose Q amount of charge is flowing with a potential difference dE. In that case, the work would be electrical and it would be equals to Q into dE, where Q is the amount of the charge and dE is the difference in their potential. Okay. Now let's discuss about heat. So as I already discussed, that heat is a form of energy and it can be produced from work or it can be converted into work. So heat flows from higher temperature to lower temperature until the system attains thermal equilibrium. So heat is a special form of energy because most of the forms of energy can easily be converted into heat, but heat cannot be transformed into the other forms of energy. So this is a special form of energy, and this is the reason a vast amount of heat energy is stored in the universe. So now I'll discuss about some terms, some terminologies which we used very frequently in thermodynamics. So one of them is system and surroundings. So what is system? System is the part of the universe that is selected for thermodynamic study, and this is separated by a definite boundary, either real or imaginary. Obviously, the rest part of the universe other than system is called surroundings. Let me give an example. So in this case, we have put a beaker which contains some water or something within a closed vessel. So this is the system over here, and the rest is the surroundings. So system and surroundings, both of them combines to make the universe. Okay, system plus surroundings equals to universe. So system can be of two types, homogeneous and heterogeneous. As you know from these names, homogeneous means uniform, heterogeneous means not uniform. So homogeneous systems example are mixture of gases like carbon dioxide, oxygen, nitrogen, any gases. Generally, most of the gases they are miscible. They form one phase. They cannot be separated. So mixture of gases they are an example of homogeneous system, and mixture of miscible liquid like water and methanol. They will form one phase and they completely mixes with each other. So mixture of any miscible liquids and pure solid. Similarly, example of heterogeneous system is obviously which forms two three phases. Like if we mix liquid and vapor, they will form two different phases, so they are heterogeneous. If we mix two immiscible liquids like water and suppose ethyl acetate, they will form two layers, so they are heterogeneous. Mixture of solids, they are also an example of heterogeneous system. Let me show this here. So mixture of gases, this is one phase system, and this is the example of homogeneous system. And mixture of liquid with vapor, this is a heterogeneous system, and this forms two phase. Okay, so now we'll discuss about different type of systems. So the systems has been classified into three different types. One is open, closed, and isolated. So let's discuss them one by one. So what is the open system? So whenever both mass and energy can be exchanged between the system and surroundings, this is known as a open system. So example, any chemical reaction occurring within a beaker. We are doing any chemical reaction in an open atmosphere. Sometimes we close the beaker. No, in this case, we will not close the beaker. We have added some chemicals. We have added a solvent, and we are doing the reaction within a beaker with open atmosphere. We have not closed it. So this is an example of open system. This is the pictorial presentation of an open system. So both mass and energy can be exchanged between the system and the surroundings. And this wall of the system is known as permeable wall, as it allows the exchange of both mass and energy. Next, we'll go to closed system. So in this case, energy is exchanged, but not mass is exchanged between system and the surroundings. So example of this is liquid and vapor in equilibrium within a sealed tube. So we are not allowing the exchange of mass, but energy is being exchanged. So this is an example of closed system. So this is the pictorial presentation, and this particular wall is known as dithermal wall, as it allows the exchange of energy but not the mass. Next, we will go to isolated system. In this case, neither energy nor mass can be exchanged between system and surroundings. Example is water or any liquid within a thermal flask, like insulated flask, where we do not allow any mass or energy exchange. So this is the pictorial presentation of an isolated system, and this wall is known as adiabatic wall, as it doesn't allow the exchange of mass and energy. Okay, so as I already mentioned, the example is water within a thermal flask. Okay, so these are three different type of systems. So interaction of open system, obviously interaction of open system with the surroundings is maximum because we are exchanging both mass and energy, while in case of isolated system we are not exchanging anything, so the interaction between system and surroundings is almost zero. Okay, now we'll discuss about the measurable properties of a system. We broadly classify them into two different types. One is extensive, another is intensive. So, what is extensive property and intensive property? Extensive means the properties which is dependent on the amount of material present within the system, like volume, mass, heat capacity, mole number, and many thermodynamical properties like enthalpy, entropy, work function, free energy. I'll discuss the thermodynamic properties later on in this series. So, all these properties, they are dependent on the amount of material present within the system, like the volume. If we have taken a little amount of water, the volume will be less. But if we taken a large amount of water, the volume will be higher. Same is the case for mass. Mass will also change if we take little or if we take more. Heat capacity, that will also change. Mole number, that will also change. I will discuss later on about these thermodynamical properties. So let's go to the intensive properties. As you can see from the name itself, intensive means independent on the amount of material present within the system. So some typical examples are temperature, pressure, density, refractive index, viscosity, surface tension, concentration, and molar properties. So if we take a small amount of water or we take a large amount of water, the temperature will be same, pressure will be same, density will be same, refractive index will be same, and all these properties which are intensive properties, they doesn't depend on the amount of the material present within the system. Okay, so next we'll discuss about the state of the systems. So a state of a system is defined by the state variables temperature, pressure, volume, and mole number n. Okay, but for closed and isolated system, n is fixed. So because we are not allowing the exchange of mass, so n is fixed. So out of pressure, temperature, and volume, only any two can describe the state of the system. So for closed or isolated systems, state of the system is described by either temperature volume or temperature pressure or pressure or volume. TP, TV or PV, and N is fixed. So any change in the values of these state variables will change the state of the system and it will attain a new state. Suppose we had a system having temperature T1, volume V1. So we are changing either temperature T1 to T2 or volume V1 to V2, or we are changing both of them together. In that case, the system will attain a new state. and we will call this initial state to final state, or it may be some intermediate states, but the state will be changed if we change any of these variables or both of the variables. If we bring the system back to its initial state, these state variables, they will get back their original value. Suppose we had a system with temperature T1 and pressure P1, and then we had changed the temperature T1 to T2, but suppose we didn't change the pressure, so it has reached a new state T2 P, and P was there. So it was T1 P, the initial state, and it has reached to a new state T2 P. So whenever we change our temperature from T2 to T1, it will come back to its initial state. So the temperature will get back its original value, which was T1. Okay. So next we'll discuss about path. Path is the sequence of intermediate steps which takes a system from initial state to final state. So let me discuss this. Let me draw this for your better understanding. I'll draw this. Let me share the whiteboard. Sorry for this. So this is I'm drawing two axes P and V. So suppose this is P2, this is P1, and suppose this is P1 and this is P2. Okay. So let me describe the states. So what is this state? This is defined by P2, P1. Okay, and this state, this is P2, P2, and this state, this is P1, P2, and this state is obviously P1, P1. Okay. So our system was initially in this state P1, P1. Now if the system we want to reach to P2, V2, we have three different paths. As I discussed, that path is the sequence of intermediate steps which is needed to reach a system from initial state to final state. So the initial state of the system is P1, P1, and we want to reach to P2, P2. Now the system can go through different paths. So for path 1, what is the path 1? First, increase the volume from P1 to P2 at constant pressure. Okay, you will do this at constant pressure. So what will be that? So P1 V1 to P1 V2. So the system first travels in this direction, and then will decrease the pressure P1 to P2 at constant volume. So then in this case the volume is V2 and pressure is decreasing from P1 to P2. So the system reaches in this state. So we have reached P1 V1 to P2 V2, and then there could be a path 2. Suppose we are first decreasing the pressure P1 to P2 at constant volume. So in this case, P1 is being decreased to P2, but volume is constant. So in that case, it will travel from P1 V1 to P2 V1. So in this state. So next, the volume will increase the volume of the system from V1 will increase the volume, will decrease the volume of the system from V1 to V2 at constant pressure. So it will reach from P2 V1 to P2 V2. Okay, and then there is a path 3. So in this case, we can do this simultaneously. Like we'll increase the volume V1 to V2, and at the same time we'll decrease the pressure from V1 to P2. So we are doing this together simultaneously. So there could be a direct path from P1 V1 to P2 V2. So these are 3 different paths. Okay. So I hope you understood what is called state and what is called path of a system. Now I want to uh, mention the thermodynamic equilibrium and steady state. Let me go back to my slides. Okay, so let me go back to the thermodynamic equilibrium and steady state. So what is thermodynamical equilibrium and what is steady state? Whenever the state variables, temperature, pressure, and chemical composition of a system remains time invariant, the system is under complete thermodynamic equilibrium. That is, it satisfies thermal, mechanical, and chemical equilibrium at a time. So the state variables, if the state variables of a system is time independent, the system is under thermodynamic equilibrium. But in case of an isolated system, whenever there is no exchange of mass and energy between the system and the surroundings, the isolated system is in equilibrium whenever its macroscopic properties remain time invariant. But in case of a non-isolated system, it will be in equilibrium when it satisfied 2 conditions. So what are those 2 conditions? Condition number 1, all of the macroscopic properties of the system, they remain time invariant. And secondly, if we distract the system from its surroundings, there is no change in the properties of the system. So this is true for non-isolated system, that is whether if system is open or closed. As I discussed in my previous slides, that both exchange of mass and energy is allowed for a open system, and only energy exchange is allowed for a closed system. So for this open and closed system, If the system has to be in equilibrium, it has to satisfy these two following conditions. Condition number one is the macroscopic properties has to remain time invariant. And condition number two is that if we detach the system from the surroundings, there will be no change in the properties, internal properties of the system. In these two cases, if these two criteria are satisfied, we can tell that the non-isolated system is in thermodynamic equilibrium. But if we, for a non-isolated system, we are fulfilling condition number one, but condition number two is not being fulfilled, in that case we will just tell the system is in steady state, but it is not in thermodynamic equilibrium. Okay. Okay, so I'll discuss about more details uh, about the thermodynamical properties, the second law, and more other mathematical forms. So I'll discuss them one by one in my thermodynamics lecture series. So please like, share, and subscribe. And if you have any question, you can ask me in the comment section. I'll try my best to answer them. Thank you. Bye bye.